Uh-oh, uh-oh, uh-oh. Thanks. All right. So vectors are arrows with both magnitude and direction. Okay. So really a quantity. Okay. Um, Here are some pictures of vectors. These two vectors are equal because they are in the same direction and they are of the same magnitude, aka length. Magnitude means length. Okay? These vectors have the same length, but they are going in opposite directions. So we could say that they're parallel, okay, but they're going in opposite directions, so they're not going in the same direction. Okay? These vectors are of the same direction. They're going the same way, they're parallel, but they are of different magnitudes. One is longer than the other. Okay? And these two vectors have nothing similar about them at all. They're going in different directions. They do not have the same magnitude. Now you did a little bit of vectors in geometry, correct? That was a long time ago. Some of you have worked with vectors in physics. All right. We can place vectors anywhere, okay? But it is going to be easier to think about vectors when they are in standard position. Okay? A vector in standard position means it is drawn from the origin. It's easier for us to think about what that vector looks like if it's drawn in standard position, where its tail or initial point is at the origin, and then it's drawn from there. We call this the initial point. What would we call that? The terminal point. Because we start at the initial point and our arrow is drawn to the terminal point. There's going to be two different ways to write vectors. Okay? Do you remember seeing those chevrons used in the book? Okay, they didn't look like parentheses, they were like half triangles basically. Okay. The first way we're going to write vectors is in component form. Okay. Now, if I want to figure out what standard form is, okay, our vector is drawn from initial point to terminal point. So if we want to figure out what our standard form is, we have to take our terminal point and subtract our initial point. Okay? And we're going to do that for each x and each y. So we're going to take terminal minus initial for x and terminal minus initial for y. And it's going to give us a coordinate, but we're not going to write it as a coordinate because we're going to use these chevrons, and that means it's a vector. So this is the vector that we are going to write in component form. Okay, what's the x component? What's the y component? So we have a point of 2, -5, and a point -1, 3. So there's our vector, initial point, terminal point. In order to write our vector in component form, okay, we're going to take terminal minus initial for the x's, so -1 minus 2, and then terminal minus initial for the y's, so 3 minus -5. What is our x component for this vector? -3. What is our y component for this vector? 8. So this is our vector in component form, which means to graph this in standard position, we begin as 0, 0. Our horizontal component is -3. Our vertical component is 8. There's our vector. -3, 8. Horizontal component, vertical component. It's like you're plotting the coordinate and drawing an arrow to it. Okay, we need to talk about magnitude and direction. Okay, magnitude meant what? Length. Okay, and it has a weird symbol there. So anytime you see the double absolute value, okay, when we're talking about vectors, that means it's referring to its magnitude. Okay, so you're going to see a lot of U and V and W as names of vectors. You will also notice when they name a vector, it's going to be bolded in your book. Okay, when we name vectors, we name them with a bold letter. Okay, I won't make you bold your vectors with your pencils. Okay, that's kind of difficult, but just know that that's what's going to happen. So I'm going to, in general, name my vector B to be, my vector V to be AB. That means when I plot it in standard position, we go over A and up B to draw our vector. Okay? Now, I want to know what the length of that vector is. How could I do that? The Pythagorean theorem. So this is the length of our vector. So Pythagorean theorem would be a squared plus b squared equals magnitude squared. Okay? Or in other words, our magnitude is the square root of a squared plus b squared. Okay? You can remember the Pythagorean theorem, or you can remember this formula, which is the Pythagorean theorem. Okay? Biggest thing here is the notation. So on our last slide, we had vector u was -3/8, correct? Okay. If I want the magnitude of vector u, which is -3/8, we'll take the square root of the x component squared plus the y component squared. What is our magnitude? Sarah, you were saying you weren't? Say louder. square root of 73, right? Because we have 9 plus 64, okay? We do not say plus or minus because we're not square rooting both sides of the equation. Okay, so it's only going to be positive. And we're talking about length, and so it's going to be positive anyway. Okay, so 9 plus 64, square root of 73. Okay. All right, let's talk about adding vectors. Okay, so Morgan already pointed out that she really liked the parallelogram addition. Okay, there are two ways that we can add vectors: the parallelogram addition or the tail-to-head addition, which you saw pictures for in your reading last night, correct? Okay. I'm going to start with the tail-to-head addition. Okay. If I'm adding two vectors, u plus v, then what you can do is you can take u, let's say it's this vector, and then where u stops, that's where you're going to begin with v. So tail to head, where the head is of the first, the tail goes for the second. And then if you connect the tail of u to the head of v, there is u plus v. Okay? That's what it looks like for tail to head addition. Okay? What about parallelogram addition? So here is u, and here is v. They're going to be drawn from the same initial point. If you make a parallelogram out of those two vectors, then its diagonal is your resulting vector. Okay? Same picture, different ways of thinking about it. Okay? Let's actually get some numbers involved. Okay? If I asked you to add together vector u, which is 2, 3, and vector v, which is 4, 1. Layton, what do you think u plus v would be? What do you think u plus v would be? If you just had to guess. If this is vector u and this is vector v, and we add them together, what do you think we would get?
6, 4.
You think we would get 6, 4. What do you think? All we have to do is add components, okay? We have the vector 2, 3. We're going to add the vector 4, 1. So over 4, up 1. Okay, if we look at tail to head addition here, here is our resulting vector. We add our horizontal components, we add our vertical components for our new vector. Okay. Along those same lines, u minus v. Matthew, what would that equal?
2,
Careful, u minus v.
-2.
-2, 2. We take u and we subtract out each component of v. Okay. Now, I want you to understand that we're not really subtracting these two vectors. We're actually adding the opposite of v. Okay. We're basically adding -4, -1. It's going in the opposite direction. So we're taking 2, 3, okay? And we're adding -4, -1. We get our resulting vector -2, 2. So this is u, and this is -b. Okay, does that make sense? Okay. One more. 4v. Courtney, what would 4v equal? Here's v. If you had to guess. 16/4. Okay, you just multiply that scalar through. What's really happening? You're taking v and you're adding it together 4 times to get your vector of 16/4. Now, these properties are in your book. Don't write them down. Refer to them. You can probably already assumed them anyway. Vector addition is commutative. When you add the 0 vector, you get it back. Okay. Associative property, you can multiply in any order. So C and D, those are scalars. Okay, we don't know how to multiply vectors right now, but we'll learn that in a couple days. Okay. Distributive property, if you have a constant multiplied to your vector, then its magnitude is the same magnitude with that constant multiplied to it. Okay. Associative property with addition, adding the opposite vector is going to get you the 0 vector. Distributive property here again, u times 1 is u times 0 is a 0 vector. Do you notice how things are bolded and like C and D, those are not bolded? It's because the bolded, those are vectors, the non-bolded, those are constants or scalars, however you like to think of them. All right, we have talked about magnitude. Now we need to discuss direction. Okay. Direction is the angle that is made with the positive x-axis. Okay. So in this case, my picture right now is drawn in the first quadrant. Okay. If, to draw this, we go over the length of A, up the length of B, how will we ever be able to figure out what that angle is?
Trigonometry.
Okay, let's erase that sarcasm. Kyler, what would we really do?
Trigonometry.
Which trigonometry?
Tangent, inverse tangent.
Okay, we know that the tangent of theta needs to be opposite over adjacent, right? So, if we have the vector 5, 4, over 5, up 4, okay? If we have the vector 5, 4, we need to figure out what that angle is. So we're going to take the tangent of theta and set it equal to opposite over adjacent, or B over A. You can draw the picture every time, or you could remember that it needs to be Y over X, B over A. Okay? With your calculators, please take the inverse tangent of 4/5. What did you say? Can you please confirm this angle? Yes? Okay. We drew our vector in the first quadrant This makes sense, right? Okay, now, where you need to be careful is when our vector has its terminal point in a different quadrant, okay? So what if I wanted the direction of negative 3, 8, our vector from before? Okay. Well, negative 3, 8 lies where? Okay. Negative 3, 8 lies in the second quadrant. Okay. Technically, we want to find this angle for the direction between our vector and the positive x-axis. That is our direction. But what we're going to have to do is we're going to have to figure out this angle first. Okay? We're still going to take the tangent of theta equals what? Eight over 3. I'm going to keep it as positive. If you write, you know what, we'll do it as negative. Okay? It won't matter. What is the angle you get when you take the inverse tangent of 8 over negative 3? Okay. What did you say, 69 point what? Does that make sense? That makes sense for our second quadrant angle to be in that direction. No. What our direction really is 180 minus 69.44 degrees. No, if you remember, inverse tangent is only going to give you an angle between negative 90 and positive 90. So if you have a negative A or B, it's going to give you a negative reference angle. It's basically what's happening, okay? When you do the inverse tangent, it's going to give you a reference angle, whether it's going to give you a positive or a negative value, okay? It doesn't really matter. That's why I said I was going to leave the negative off. The negative really doesn't matter. It just tells you which quadrant your vector is in, okay? So our reference angle is 69.44 degrees. Since we're in the second quadrant, we're going to take 180 minus 69.44 degrees. And our direction is really 110.56. All right, let's talk about that unit vector that, Layton, did you bring that up? Yeah, Layton wasn't excited about the unit vector, okay? We've heard the word unit before. We have a unit circle. What did that unit mean? 1. Okay, in our unit circle, what was 1? The radius, okay? In our unit vector, our magnitude is 1. Okay, so first what I want you to write down is that a unit vector is a vector with magnitude 1. Now unit vectors can be very helpful. Okay, so sometimes, later on, it's going to be nice to take a vector and figure out what the unit vector is in its same direction, so that we can do something else with it. So if I want a vector to have a magnitude of 1 but keep its direction, this is what we're going to do. Okay, we're going to take the magnitude and say 1 over the magnitude times our vector v, and it gives us a new vector. We find the magnitude of our original vector, and then we multiply our vector by the reciprocal of its magnitude. Okay. Why does this give us a unit vector? If we think about finding the magnitude of this, What's the magnitude of v? We write it like that, right? This is a scalar that we're multiplying to it. What happens when we multiply those? We get 1, okay? So that is why we get a unit vector out of the deal. So let's go back to our vector, negative 3, 8. Okay. What was the magnitude of negative 3, 8? So its magnitude was radical 73. So our unit vector, okay, is going to be 1 over radical 73 times negative 3, 8. Which means we have negative 3 radical 73 over 73 and 8 radical 73 over 73. There's our unit vector. It has the same direction as negative 3, 8, but it has magnitude 1. In your reading, do you remember reading some I's and J's? Nat, you're shaking your head yes. Do you remember what those I's and J's were? Okay, so I's and J's, those are some special vectors for us. Hold on, I'm trying to think of our time here.
5 minutes.
Yeah. Do you want to do another unit vector problem? Okay. I forgot I had this example. I just did the example of the vector that we already had been working with. So, I'm sorry. I's and J's. Okay. So, this is going to be the second way we can write vectors. So first of all, let me introduce to you vector I and vector J. Vector I is the standard unit vector 1, 0. Okay. It's a unit vector that is just horizontal. Vector J is a unit vector that just has a vertical component. Okay. So using these vectors, we can write our vectors in a different way. Okay. Notice how I and J are bolded because they're the names of vectors. Okay. So our vector negative 3, 8, we can write as negative 3 I plus 8 J. It's the linear combination of the two. So you're adding these two together. Now, why does this work? Remember, I is the vector 1, 0. Plus J is the vector 0, 1. So by the end of this, you're getting the vector negative 3, 8. Okay? But you have to have that addition in between. Okay. If we think about it backwards, 4I minus 3J in component form would be 4 comma negative 3. It's just a different way to write our vectors. questions on the INJ? So I had some problems. We'll only maybe do like one or two of these. If this is P and Q, please find me the component vector PQ. It's the vector PQ. Yes.
Negative 9. Wait. Negative 9.
Sean says -9, -1. Do you agree with Sean? Since it's the vector PQ, Q would be considered the terminal point and P the initial. So we have to take terminal minus initial. So Q minus P. We have to work backwards essentially. Okay. Let's go to the fourth one. If I wanted this in linear combination form, Michael, how would we write it?
I don't remember what that is.
Okay, linear combination form is with the i's and j's.
So that -9, I, -1J.
Okay, good. It just needs to be subtract 1j. I want you to make sure that you are taking, like, it's an addition. Okay, it's a combination. There's no comma. Where the comma is, you should have addition there. Okay, so here is your homework. Okay, tomorrow we'll continue and we'll look at more of some applications of what it means to add vectors. Okay, we're going to work with some forces tomorrow.
Really? I'm excited.
Are you excited? It'll be fun. Make sure you have your calculators tomorrow and every day. I mean, you need them throughout this entire chapter, so.